Rockets are awesome, but let's be honest, they're a brute force, barely controlled explosion. 90% fuel, 1% payload, and they explode, cost a fortune, and are wildly inefficient. Imagine a vertical train climbing a super strong cable from the ocean all the way to geostationary orbit, 22,000 miles up. This is the space elevator. Thanks to materials like carbon nanotubes, this wild idea is now theoretically possible. Arthur C. Clarke said the elevator would be built 50 years after people stopped laughing. Well, the laughter is fading. So, are we ready to climb? Today, we're not launching. Today, we climb. The idea of reaching space with a tower goes all the way back to 1895, when the Russian scientist Konstantin Tsiolkovsky gazed up at the newly built Eiffel Tower. Inspired by its soaring iron lattice, he imagined a structure that could stretch all the way from the ground to the stars. A tower so tall, it would reach into orbit. At the time, this was pure science fiction, a dream that seemed as impossible as flying to the moon. But as engineers and scientists soon realized, building a tower up from the ground to space isn't just difficult, it's physically impossible with any material we know. The base would have to support the weight of thousands of kilometers of structure above it, and would be crushed long before it ever reached the edge of space. The breakthrough idea came decades later. Instead of building up, what if we built down from space? Place a satellite in geostationary orbit, and then unspool a cable all the way down to Earth's surface. In this design, the cable is held perfectly taut, balanced between two enormous forces: gravity pulling it down toward Earth, and centrifugal force from the spinning satellite pulling it outward into space. It's like a cosmic game of tetherball, with the cable stretched tight between the planet and the satellite. Instead of a massive tower being crushed under its own weight, you have a slender ribbon, pulled tight by the laws of physics, creating a permanent, stable link between Earth and the heavens. The base on the ground doesn't need to support the weight of the whole structure, it just anchors the end of the cable. All the tension is distributed along the cable itself, stretched from both ends. This elegant solution flipped the problem on its head. Instead of an impossible tower, the challenge became a search for a material strong and light enough to survive the incredible forces along the cable's length. For a long time, that material simply didn't exist. Scientists and engineers could only dream of fibers strong enough to make the space elevator a reality, waiting for technology to catch up with imagination. Imagine a cable so strong it could stretch from the surface of the Earth all the way to geostationary orbit, over 22,000 miles up, without snapping under its own weight. Not only must it support itself, but it also needs to carry the weight of climbers, cargo, and the constant pull of gravity, all while remaining under unimaginable tension. This is no ordinary engineering challenge. It's a test of the limits of material science and human ingenuity. Steel, the backbone of our bridges and skyscrapers, would snap under its own weight long before reaching orbit. Kevlar, famous for stopping bullets, isn't even close to strong enough for this task. Even our toughest materials fall short by a huge margin. What we need is a material that's dozens, even hundreds of times stronger than steel, yet as light as plastic. For decades, this was pure science fiction, a dream that seemed impossible, with nothing in existence that could come close to meeting these extreme requirements. Everything changed in 1991, when Japanese scientist Sumio Iijima discovered carbon nanotubes. These tiny cylinders of carbon atoms are the strongest material ever found, tensile strength beyond anything previously imagined. In theory, a ribbon made from carbon nanotubes could support the weight of a space elevator, making the impossible suddenly seem within reach. Carbon nanotubes are over 100 times stronger than steel, yet weigh just a fraction as much. Their unique atomic structure gives them incredible strength and flexibility. But there's a catch. So far, we can only manufacture nanotubes a few centimeters long in the lab, nowhere near the 22,000 miles we need. And there's another problem. To work, the ribbon must be flawless. No weak spots, no defects, not even a microscopic crack. Any flaw could cause catastrophic failure, snapping the entire cable in an instant and bringing the dream crashing down. The material exists, at least in theory, but manufacturing it at the scale and perfection required is humanity's next great challenge. Creating this magic string is possible, but the technology to produce a flawless, continuous ribbon stretching to space is still out of reach, for now. The dream of a space elevator is alive and inspiring a new generation of scientists and engineers. The work is just beginning, and the unbreakable string may one day become a reality. Imagine for a moment that we've finally engineered our carbon nanotube ribbon, a marvel of material science, thinner than a human hair, yet strong enough to stretch from Earth's surface all the way to geostationary orbit, 22,000 miles above. This is the backbone of our space elevator dream. But how do we actually climb this impossibly long ribbon? Enter the Climber, a self-propelled elevator car designed to ascend the cable with precision and reliability, carrying cargo and perhaps even people into space. The Climber grips the slender ribbon using advanced rollers, likely coated with diamond or other ultra-hard materials, to minimize wear and maximize grip. These rollers pull the vehicle steadily upward, overcoming gravity's relentless pull. Instead of carrying heavy fuel, the Climber receives power beamed from the ground, using high-intensity lasers or microwaves. These energy beams are captured by the Climber's solar panels and converted into electricity, which drives its powerful electric motors. The challenge? The laser must track a moving target thousands of miles away, through shifting clouds and the ever-changing atmosphere. Maintaining a precise, uninterrupted energy link is a huge technical hurdle. The ascent is slow and steady, about 120 miles per hour. It's not a quick trip. The journey to orbit takes nearly a week, as the Climber methodically inches its way up the ribbon, high above the clouds. Inside the Climber, the ride is remarkably smooth. There are no crushing G-forces, no violent shaking, and no roaring engines, just a gentle, continuous motion upward, like gliding in a luxury elevator. As you ascend, you'll watch the Earth slowly shrink beneath you. The blue sky fades to black, and the curve of the planet becomes visible, a breathtaking, ever-changing view from your window. The Climber itself is a self-contained habitat, equipped with life support systems, food, water, and everything needed for the week-long journey. It's a moving home, designed for comfort and safety as you travel to the edge of space. This isn't a rocket launch, it's more like a train ride, an extraordinary, peaceful journey to the stars, opening a new era of access to space. The cable must be anchored at the equator, where Earth's rotation keeps it stable. Most of the equator is ocean, and land sites are risky: storms, lightning, and political instability. The solution? A massive floating platform, like a mobile oil rig, anchored in calm, equatorial waters. If a hurricane approaches, the platform can move out of the way. Space debris is a threat, so the platform constantly shifts, dodging incoming junk using satellite tracking. The anchor isn't fixed. It's a moving oceanic base, dancing to keep the cable safe. It's an elegant answer to weather, politics, and orbital hazards. What if the cable breaks? It's dramatic, but not apocalyptic. If it snaps near the bottom, the lower half rises into orbit, not falls. The upper half, with the counterweight, is flung outward into space. If it breaks in the middle, the upper part flies away. The lower part falls, but it's so light it burns up in the atmosphere like a slow meteor shower. The danger on the ground is minimal, less than falling rocket debris. It would be a financial disaster, but not a world-ending event. The cable is designed to fail safely, not catastrophically. The real risk is cost and time, not planetary destruction. This isn't just sci-fi. Japan's Obayashi Corporation wants a working space elevator by 2050. Their plan: a 60,000-mile carbon nanotube cable, robotic climbers, and a massive orbital terminal for research, tourism, and solar power. From the top, launching to the moon or Mars is easy. Just let go at the right time, and you're flung outward. They even envision a Mars Grand Elevator, creating a logistics superhighway between planets. The cost to move material between worlds would plummet, enabling cities on Mars and asteroid mining. Experts doubt the timeline, but the fact that real companies are planning means the laughter has stopped. It's not if, but when and how. A full space elevator is tough, but there's a stepping stone. The skyhook, or rotavator. Picture a much shorter cable, orbiting and spinning end over end. A hypersonic plane hooks onto the tip, and the skyhook flings it into orbit. The material demands are far lower. Kevlar or Xylon could work. We could build a skyhook with today's tech, dramatically lowering launch costs. There are rotating and non-rotating versions, each with unique advantages. Rendezvousing at Mach speeds is hard but solvable. Skyhooks could bridge the gap to a true space elevator, making space access routine. Earth's elevator is hard, but the moon's is much easier. Lower gravity, no atmosphere, and existing materials like Xylon are strong enough. A lunar elevator would stretch from the surface to the Earth-Moon L1 point, about 35,000 miles. No storms, no atmospheric drag, and solar power is easy. The moon is rich in resources. An elevator would make mining and exporting materials cheap. L1 is a perfect staging area for missions deeper into the solar system. We could build a lunar elevator with today's technology, a practice run for Earth. It could be the backbone of a lunar economy and interplanetary industry. Space elevators force us to dream bigger. Rockets are for exploration, elevators are for colonization. If we want millions living on Mars, we need a bridge, a permanent, cheap way off Earth. The space elevator is that bridge, shifting us from visiting space to living there. Maybe skyhooks or a lunar elevator come first, but the dream is alive. Would you ride the stairway to the stars? Let us know in the comments. Subscribe for more journeys to the future.